I oh.
Are you here for LeetCode? Yes. Perfect. Two victims. No, I was about to leave, but we're gonna record it anyway because people view it afterwards. Just sign in and grab a sign.
Are you guys like CS majors?
No.
Oh, you just want to learn about linked list?
I was just getting. I dragged him along. I'm the one that wants to.
Ah, okay, okay.
And what major are you? Physics.
Oh, okay. What are you STEM?
I'm a physics.
Oh, you both physics.
No, I do think I don't know any data structures, so something I will learn. Linked list can be helpful even for physics. Oh no, yeah.
Yo, Ming, is there like a dry erase marker? There's just Sharpies over here. Are you guys like familiar with like just like LeetCode?
Oh yeah, I've done only like a few LeetCode problems before, but this is supposed to. I'm hoping this will motivate me more.
Okay, cool, yeah.
What about you?
Yeah, I kind of had to. Like last cycle, I was like going through interviews, like like you're familiar with like Bloomberg, right? Yeah, Bloomberg, they're really big for Princeton. I was in the New York City cohort. Yeah. So it was like 5 rounds, and 3 of them were technical. So it was a straight LeetCode for all of them, and yeah, so I kind of had to grind it. So, but so they usually, I'm gonna be honest, if you just do their tag, like it's on LeetCode, like if you just like go on their like LeetCode Premium and get their tag and just study that, like you're in a really good spot because they just love. You don't have to. I didn't pay. I just you can just like go on like Reddit or something. So someone always just posts a tag, but yeah, it's like at the end of the day, like what is LeetCode? It's just pattern recognition, like knowing the data structures, right? And then from there you can just problem. And like you guys are physics majors, like you guys are good at problem solving. So
yeah.
Oh, hopefully.
Physics kind of like demoralized you at the same time. Even after having graduated, I'm not too sure. But no, I do think good at math.
Yeah. After this, like after I teach you guys this, like at the end, you guys can just ask me about my. If you guys are interested, you guys can ask me about my process at Bloomberg, like because I ended up like getting the offer.
Yeah, I have a couple friends that are interviewing.
Oh yeah, for Princeton. Yeah. They got their offer from like.
Is it Princeton or I don't know.
New York City is full. I think like for interns is full. So now they're just interviewing for Princeton, which is New Jersey.
It's like what was it? There was some recruiter here.
Yeah.
At
the hackathon. The hackathon.
No, it wasn't a hackathon here. I think it was career work.
Oh, I see. Do you know what her name was, or him?
No, I'm just going off of what my friends.
Oh, okay, yeah.
But, yeah, I think one of my friends just went through like they ran through like 3 interviews in one day. Like,
yeah, it's super day. Yeah. But yeah, that's how they do it. First round is just it's like it's like the first 15 minutes of behavioral, and then like 45 minutes is just like a technical screen. So they'll ask you LeetCode questions and stuff, and then after that, if you pass that round, then you move on to your next round, and then that round basically if you do good, you get a super day. So if you do good in that second round, you get the third round. If you do good there, you get the fourth round, which is HR, and then from there you schedule like your engineering manager round, and then yeah. But we're gonna talk about that at the end. Ming, is it recording? Okay, cool. So so you guys are familiar with like basic programming, right? Like, you guys know what arrays are? Okay, so so you guys know arrays. So it's like, let's say we have this. Okay, this is how you represent array: 1, 2, 3, 4, and 5. Okay, so we know that like this is an array. So you guys know like how we can, for example, access this, right? Like arrays are indexable, right? So like index, like this would be like a 0, a 1, a 2, a 3, a 4. Okay, and let's say this is just A. Okay, this array is equal to A, right? So let's say we want to get this 3. Okay, how will we get it?
Well, we
Exactly. We do A sub 2, right? So this is what so arrays like this, they're very useful, right? Now, a linked list is another way to store this data. Okay. Now you might be thinking, okay, what? So this is a visual representation of what a linked list is. Okay, it's literally just a node. Oh yeah, yeah, for sure, for sure. Good. All right. So here you can kind of see the visual representation, right? It's just a node. Okay. And then so this is like the node, right? It's so this is just a node, and then there's a value inside of it. Okay. So this is going to be 1, and then this is pointing to another node, and then it just keeps on going, right? Now you might be thinking, okay, why would we do this? Okay, why not just use an array? Okay, let's give this analogy, right? Let's say, so think of an array as, let's say there's 5 people sitting in chairs, right? And they all have they're all sitting in number chairs. Okay, so let's say we want to put someone in the middle. We want to put someone in chair number 2, right? So imagine if we were, so this guy would have to sit up and he would have to move over, right? And then this guy would have to get up and move over. This guy would have to get up and move over, and it'd keep on going, right? So imagine there was like 1,000 people or like a billion people in this line, right? That's inefficient, right? Because you might be thinking, oh, we can all just get it, but like computers, like they're like babies, like they're very methodical, so it's just gonna do one by one, one by one. So that's very inefficient, right? But now let's say we had something like we had 5 people standing in a line, right? They're all shaking each other's hands, right? Okay, so they're all shaking each other's hands. Now let's say, okay, we want to put someone in the middle, right? Think about what would we have to do, like to just put that person in the middle?
just break that.
Exactly, exactly. You could literally just like break that link, and then you can just put that person, make him shake hands with the person to the left, shake hands to the right, and then bam, you didn't have to move anything. You just inserted it in the middle. So you see how efficient that was. So that's something like a reason why linked lists are very nice to use. You know?
So you're saying in like a normal array, you would have to like iterate shifting them.
Yeah, yeah. You would end up you would have to shift everything to the right.
In an array, you can append to just append. Right?
Yeah, yeah. Appending to an array. Yeah. So do you guys know about time complexity?
Yeah. Well, I don't know which. I know like your terms like O.
Right. Like big O, right? Like so. Okay. So the way time complexity works is basically it's the worst case runtime scenario of your program. Okay. So so like there's also stuff like little o, and then like like theta and stuff like you're familiar with those terms, right? That's like getting your like the worst like the best case your program runs, and like the average case, but we don't. Yeah, yeah. No, yeah, big O is worst case, and that's all we care about, because at the end of the day, it's like, yeah, because worst case is like the worst thing that could happen, and like that's just something you always have to. Exactly. It's just so like so let's just say this, right? So what is the size of an array? Yeah, this okay, this array. Okay, and if you had if I added another value, what would it be? 6. So it's like it changes, right? So we could represent it as a variable, right? So the size of this array or size of any array would be n, right? So this is the size of any array. Okay. Now let's say, so let's say we iterate throughout this entire array, right? That means that we're checking every element once, right? That would be n. So our program would take worst case O of n time, linear, right? Because it's going to be going through every single element, right? And yes, appending to the front.
How would you express it that it's linear? We say like
It,
oh no, I know that's how you would visualize it being linear, but like how would you like oh then you just say oh like
oh yeah. This is how you would write it. Make O. Yep.
Oh, so let's say it was exponential, then like how would you write that oh then
Okay, so exponential, like the function being like what?
oh let's say it's like you have to do like 2 operations on
Oh, okay, like are you talking about like, oh, what if it was like a parabola or something? Okay, so if it was like a parabola, it would literally just be whatever function you're visualizing, and then inside would be whatever. So this would be O of n squared, right? And you, yeah. This is just like it's just big O, and then you just parentheses and put whatever function you have inside. And I will tell you how we get this function. Okay, so first things first, right? Big O, we do not care about constants and coefficients. Okay, so for example, let's say, okay, so we have this array. Let's say we iterate through this. Um, I'll erase this and I'll put it back on the board later. But so this array, right? So remember how I said if we iterate through every single element once, that would be O of n, right? Now let's say we iterate it. So we iterate through it once, and then we iterate through it again. Okay. So how many times have we iterated through it? Twice, right? So now it would be our time complexity would be this O of n plus n, right? Because because we did it two separate times, not inside, right? If it was inside, then it would be n times n, which is n squared, and then that would be a new time complexity, right? That would be a quadratic, right? So this is just n plus n, right? So another way to write this is just O of 2n, right? But we don't care about this 2. This 2 is any constants and coefficients in big N, we do not care about. We drop it all. Okay? So then it will be O, it will just be O then. Okay? So that's iterating through an array, right? And yes, appending to the to like the backend array, so like appending to an array, that's O of 1. It's constant, right? Because you're not really you don't have to shift exactly, you don't have to shift anything, right? Because so if you just add a 6 right here, right, that would be fine. But let's say if you added a number, you remember how we cared about worst case, right? So you remember how we said if we add a person here, okay, it will shift everything to the right. Now, like worst case scenario is someone would shift, like we would put it over here, and then what would that be? We would have to end up, then we'd have to shift everything over, right? And it would be n. So that'd be your worst case scenario, right? So that's why we like so arrays are really useful because of their indexes, right? Now, when it comes to linked lists, we don't have that we don't have that luxury of indexes. Okay, but like it gives us other benefits. Like remember how I gave the analogy of the people standing in brick and making a link? It makes it efficient for that stuff, right? So and the way so okay, because it's not indexable. Like for example, right? If I remember how we said a sub 2 gets us 3, that's just an O of 1 O of 1 like statement like that. It's instant, right? Yeah, but like for example, let's just say we want like if we wanted the middle of this array, right? Well, what can we do? Like we can just say this. We can say R, like we can say A, and then we do like what do you think we should put inside to get like the middle of this array? Yeah, right. We'd be the length of the array divided by 2, right? Which is we can say length is n. So we just say n divided by 2, right? So this is O of 1, and that's really useful now because now we have the middle. But for example, for like a linked list, you can't do that. You would actually have to iterate like node by node until you get the middle. Okay, and there's a specific algorithm for that called it's like a tortoise and hare, right? Because so this is true. I don't have a tortoise and hare algorithm problem that we're gonna be working on, but this is just something to think about. So if you look over here, right? If you have a node, so okay, so when you think tortoise and hare, like what do you think?
The hair goes very fast and stops.
Exactly.
The turtle is
The turtle, yeah, exactly. The tortoise is fast, hare is tortoise is slow, hare is fast, right? So you can have them both start at the beginning of the race, right? The hare moves twice as fast as the tortoise. Okay, so when the tortoise moves up here, the hare is over here. Okay, okay, so let's just say this: we end up over here. Okay, this is the hare. This is the tortoise. Okay, now we go over here. This is the hare. This is the tortoise. And then you see how the hare moves up here, and then we get something like over here. So essentially, this would end up getting us the middle of the linked list. Okay, and then that, but like you see how we had to iterate throughout we end up like the hare had to go through the entire thing, right? So that would be an O of n because we ended up going throughout the entire linked list, right? Yeah. So the turtle, so the hare ends up going to the linked list, right? So you remember how I said we don't care about like the constants?
Yeah, that would be 2n.
Yeah. So like, if we say something like if we had, for example, like the tortoise, or like so the tortoise ends up going throughout the entire thing, right? No, the hare goes through the entire thing. The tortoise, I mean, the tortoise is never going to go through the entire thing, right? The tortoise is always just going to end up at like the middle, right?
Oh, if you make the hair twice.
Yeah. The hair. So because of the hair is always going to be hitting every single note. So just because of that, it's going to be O-band. Like we don't really care about the tortoise because the tortoise won't ever reach the end, but the hair does. And then we care about the worst case scenario. So if you have a program that ends up becoming O of n squared, and you have an O of n like if you're iterating through this array twice, like a nested, okay, and it becomes O of n squared, and then you like maybe do like a separate iteration. So it'd be something like this. So if you had this time complexity, uh, if you had um, if you had O, and you have like uh, n squared plus n, okay, like what do you think the time complexity would be here? It'd just be n squared, right? Because we don't, because it's the greatest function, and then we don't care about the constants and coefficients. So it would just be this. It would just be the n squared, right? So okay, so this is why linked lists are useful. They're like for that regard, right? So like this one is a really basic example. So this is just saying, hey, okay, we're given a linked list. We just want to reverse it. So now like all we want to do, right, is just change these pointers, right? So like you see in an array, like it would be very simple, right? Like you can kind of just like, if you have this array, you can kind of just start over here and just go backwards, right? But like, and yeah, like it wouldn't really make a difference because this problem can be done with an array, but it's given to you as a linked list to show you a different data structure, right? And it's like a really nice beginner problem. So let's just talk about the algorithms. Are there any questions so far, or like anything with that you might be unfamiliar with, like as a linked list?
Um, no, no question.
No questions? All right. Okay, so okay, so let's look at this, right? Okay, so let's just build this out. Okay, let's just use a smaller example. Okay, so we want to reverse this so that this ends up becoming essentially this: 3, 2, 1. Okay, so this is essentially what we want to get, right? Maybe like a easier way to visualize this would be just 1, 2, 3, but then it would just be pointing backwards, right? But this is essentially what we want to get. So how do you think we should approach it? So we're not really messing with the values of the nodes. We just care about these pointers. You see these next pointers? So how can we use these next pointers to like get our to get this? Yeah. So let's think about this, right? So you can have so let's think about this, right? So essentially, like this one ends up becoming the end of the linked list, right? So you can see this. Okay, so this link, this head. So this is called a tail, right? So the way linked list works is this is called the head, and this is the tail, right? So here, this is just kind of pointing to nothing, right? So you can just say like null, right? This is pointing to nothing, right? And if you look over here, this is pointing to nothing, right? So this is just a null, okay? Now this is a singly linked list, right? So you see, I was just one arrow. So there's also another data structure called a doubly linked list, where basically it's like, okay, this is pointing here, but then this node is pointing back to this, right? That's another data structure. It's a doubly linked list, and it has its own uses. Like for example, if you can think about it, if you can go forwards and backwards, like that gives you more flexibility, right? But so it has its own use cases. Like for example, there's a very popular problem called like LRU cache. Companies love asking. It's like, do you know what a hash map is? Yeah, it's like using a hash map and a W linked list inside of one. So I feel like it's too complicated to go over, so I'm not gonna go over it. But I'm just gonna bring it up like as a problem. So anyway, this is what this is doing, right? So you kind of see how basically it ends up like, hey, this ends up pointing to null, right? So okay, so basically we're saying, hey, every single node is now pointing to like the previous node, right? So So that's what ends up happening, right? Every single node is end up pointing to previous node. So we're saying, okay, so is there a previous node here? No, right? But it should be pointing to nothing, right? Because you see over here, the one then is pointing to nothing.
Almost like are we moving null? It seems
We're not like so we're not so don't think about like so these like nodes don't really care about them. We just care about these pointers.
yeah, but if we're flipping the direction of these arrows, then it looks like null is pointing. Null is pointing.
Oh yeah, null can't point to anything because it's just absent.
Yeah, you know what I'm saying? It's like if we're just saying just to reflect the arrows, that doesn't make much sense. But
Okay, oh wait.
like if we're flipping the arrows, just moving the direction, then it looks like an arrow is going from null to 3, but that's not true.
Yeah. So exactly, right? We don't, but think about this, right? This next, this now, it should be pointing to 2, right? The only time this is gonna be this is gonna be now pointing to null, right?
So kind of just shuffling.
Exactly. We're like
It's not just flipping, it's also shuffling.
exactly. So it's like, so hey, we could have like, hey, so we could say basically, hey, we could basically keep track of a previous node, right? So we could basically keep track of a previous. So all this is doing, right, is we're at a node, and then we're making this point at a previous node, right? And then basically this is gonna move on to this one, okay? And then this is now the previous node, right? And then this is gonna point to this, and now it moves on. And you see how it just keeps on going. And then once you get like over here, right, this is gonna point to this, and then it's gonna stop running. And then this would be our program, right? So okay, so like we know what we're doing, right? We're just kind of flipping these pointers. So how do we get about it, right? So we know that we need to keep track of like a previous variable, okay? And that so like what do you think we should? So what programming languages do you guys? Python. Okay, cool. So you're familiar with Python. All right, that's good because I do it in Python. All right. So let's just make the function. So def, okay, and we can just call it a solution. It doesn't really matter. Okay. So this is a linked list, right? So it doesn't. So we can just say uh we can kind of just look at it to see what it. So okay, so it gives us a head. Okay. So it gives us a head, and now so so this is what it's gonna look like, right? So it gives us a head, and we're supposed to return the reverse list. Okay. So we know we want to keep track of a previous. Okay. So we know. Okay, so let's just say. So what do you think we should set this previous to? Because because what ends up happening is like because this ends up pointing to null, right? This ends up becoming the tail.
Okay, all right. So if you're starting from the head.
Yeah, if we're starting from the head, exactly. So this would just end up becoming none, right? So prev would be none. Okay. Now head would be this, right? So this would just be the current. So another thing, right? If you so we want to be careful, right? So if we so we can't just use head, right? Well, we could, but it's better practice to make a new variable. Okay, and that should be pointing to this head because, like, for example, right? If we say head is equal to head dot next, okay, so meaning that this is the current head, right? This is head. If we say head is equal to head dot next, then this would end up becoming the head, right? But then we end up losing this one. So then now, like, if we were to say, okay, print ed is going to start from here. Yeah. So basically, we're basically making a new pointer, basically, and we're saying, okay, this is the head, right? We're not gonna really mess with the head, okay? We're just gonna make another one called current, okay? And then this is the one we're gonna be moving, right? So like, we'll always have access to this one, like if we ever need it again. What? Yeah. Current is the one that's gonna be moving, okay? Because let's say the way linked lists work, right, is the singly linked list is if you're over here, okay, you can't get back to this, so you'd have to. So this current basically, so this is what we're going to be working with. This is what we're going to be moving. The head is going to be staying over here because if we ever need it again, then we don't want to mess with it, right?
Like if we're going through a process that was going through each node and we already went through it with current,
Yeah.
But we want to go back, we'll use head.
If you want to go back, right? If you want to go back, then what you would do is you would now make a new variable called like something else like current2, and then you would set it to head because now you have access to the start. So then you can do it again, right? But like you can't go back. So that's why you can just kind of save it. Don't mess with like the head. Just kind of make a new pointer and then just use that pointer. So we're going to be just calling it current. Okay. So we know what the previous is. We know what the current is. Okay. So so we know this is going to take a loop, right? So do we know how long this loop is going to take? So it's O(n), right? But it's like so like like when to use for loops, like when to use while loops, like
For loops is when you know how many.
exactly.
While
It's
you don't.
why is and like so we don't really know the size. So another thing about linked list, yeah. Unless like there's like a size instance variable, like when you create your node class, okay, you're not gonna know the size. Like in LeetCode, they don't give you the size of the linked list. You'd have to find that out, okay? Which is
Imply that you should use a lot.
yeah. So yeah, we would have to use a lot because we don't know the size of this, right? So we're gonna say this, right? While so when do we want this program to stop running? When it gets to the end, right? Like when it gets to this 3, because this 3 is now going to be going here, and then once this points to the 2, we're done, right? So we're going to be saying just while current, right? So this is just saying while current is not none. Okay, so we can say the same thing. It's like while current is not none or while current. This looks prettier. It's nicer, right? Because it's just saying, hey, while current, right? While it still exists, let's just keep this program running. Yeah. This is eventually. So it's gonna get over here, and it's gonna stop. It's gonna stop the program. So then and that's good, right? When it gets to none, and we don't care. Okay. So while current. Okay. So let's think about this, right? So let's say we want to switch this, right? So we know we want to get this 1 pointing to that previous. Okay. But if we do that, okay, let's just say we do that. We say this is now pointing to none. Okay. We lose the connection here. So it's like, how do we get this 2? So this is the previous, right? The previous is over here. Previous is over here, right? So so what we've broken this link. So now there's no way for us to get to this 2. Okay? But let's use that idea I gave you. Remember when I was talking about current, like that, let's make a new pointer. And then we can save that. We can save that link. So basically we can say, hey, before we break this link, you know what we can do? We can create a temporary variable that points to this, a temporary pointer. Okay? That so basically this is now the temp. So so now we know this is the next one, right? So then basically this makes it so, hey, when we do break this link and we make it this point to none, we have access to this, right? Exactly. And then we have this, right? So now this is pointing there. And now, hey, this temp could now be our new current. So we can now move our current up here, right? And then basically, so now we're over here, this point none. And then now look, and then we can move the previous up, right? So previous would be whatever this is. So this would be previous now. And then we would keep on doing the same thing. We do the same logic. This would now, we store it. So this would be temp, right? Okay, we would make this point back over here. Okay, prev, we would end up moving up here to whatever current is, right? So prev is over here. And then so now we have this. We break this link, but we don't care, right? Because we have temp. And then so now we're done with this. Now we go to current. So now, so current is equal to temp. So now we're over here. Okay. Then we do the same thing. Hey, let's point this back here. Okay. We're gonna be breaking this link, right? Because temp is now over here, but it's not gonna keep on going, right? So we can break this link. Doesn't matter. And then bam, we reverse it. Now it's 3, 2, and 1, right? So like that works. Like that's so. Would you prefer me to write out the code on the LeetCode problem, or let's see what it looks like? I hope there's okay. I'm gonna have to sign in. What happened? Oh yeah, sure. Let me just sign in. I get the password right. Okay. You said you want to see how many problems I got solved?
Literally just flex it for 1 second.
It's not a flex. This is so bad. 381. Yeah. But okay, so let's go to Python. I hope. Okay. Oh, nice. It cleared it. Okay. So we kind of already have the stuff set out here. So we can say prev is equal. Oh yeah. Let me. Sorry. Yeah. Okay. Prev is equal to none. Right. So we know this. Okay. We can say current is equal to head. Head is what they give us, right? Optional list node. Okay. So we can say, hey, while current. Okay. So remember. So you remember our algorithm? We want to. What should we do first? We don't want to break that link. We don't want to break that link yet. First, we want to save that link, right? So we should make the temp, right? Exactly, temp. Okay. So temp is equal to what? Okay. So we could say yeah. So yeah, what's essentially happening, okay, is hey, let me just redraw the original one. Okay. 1, 2, okay, 3, right? So hey, we want so previous is over here, okay, and this is current over here, okay. Yeah, so temp would have to be this, right? Yep. So okay, so we say temp is equal to current dot next, okay. So now we have this link, okay. So now we can update it, right? So now we can say current dot next, right, is now equal to prev, okay, and then we can say hey. So now we've broken that link, right? So now we've switched it, okay. So now we can say current. So current is still over here, right? So now we can update our previous, right? So now we can say prev is equal to current, right? So then that would end up getting over here. So this is our new previous variable, right? And then now what do we want to do with our actual current? Our actual current is still over here. To temp. Okay. Current is equal to temp. So this effectively gives us our entire thing. Now I want you to like the thing, right? So I called it so we can just call it previous, right? Because that's what ends up becoming, right? So yeah, so I forget because W linked list there's also like a prev. So like over here there's a self dot next dot is equal to next. For W linked list there's also usually like self dot previous is equal to previous. So that's why I was like, oh wait, we can call it temp. It doesn't matter. Temp, 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 temp. Okay. So now let's just run through this, right? So here we're basically storing that link. We're saying okay, we want to save that link. Okay. Now here we're saying we're breaking that link now. Okay. We're saying now this current.next it should be pointing to the previous, right? What was previous before, or temp? It was none, right? So you remember this ends up becoming the tail, and tail always points to none, right? So then okay, we've done that. Then we go over here, right? This temp, okay, it's now equal to current. So basically we're saying, hey, okay, so now we're saying, okay, this temp, okay, we're basically moving up to whatever current was. Did I do this right? Temp is equal to current, current.next is equal to temp, okay? Yeah, so okay, wait. So let's get rid of this, okay? So we know that this temp is equal to current.next, okay? We've saved that link. We're saying current.next is equal to temp. So now we're saying this goes back, okay? So now what do we want to do, right? We want to update our current, right? So our current should now move up, whatever. So we can say current is equal to temp, right? And then what do we want to do with our temp? Yeah, so our temp, right? So we would actually have to put that before. right? We'd have to put that before because if we say temp current is equal to temp, then that means we're saying previous is this, and we don't want that. We want to do it from before. Okay. So what ends up happening is when you run through this entire program, temp ends up becoming your new head. It ends up becoming your new head. So then if you want to return it, we just say like return temp, and then like run this. I didn't mess up anywhere. Oh yeah. So okay. So here we have it here. So current is equal to temp. What did I do wrong? Oh yeah. So we're basically saying current. Hmm? No. Look. So let's do this, right? So previous is equal to 9, right? I'm just gonna do it because this is what we're used to. So we're saying while current, right? So we want to store that link. Temp is equal, or prev is equal to current. Oh, you know why it wasn't working? Because temp has to be on its own thing. All right. So temp is equal to current.next. Okay. So now we're gonna be breaking the link, right? So we're gonna say current dot next is equal to prev. Okay. And then after that, we're gonna be updating, right? So now we're gonna be saying, okay, prev is equal to current, and then current is equal to temp, and then we can return, and then our previous would now be our new head. So let's run this. This should run. Yeah. So yeah, this works. This submits. I just got caught up in the variable names. But
So when going down all the nodes, it goes temp, and
Mhm.
it goes. So the temp goes first, right? You know how you're.
yeah, temp. We want to store. We want to store that link.
I guess it's related to like the hair.
Oh no, torsion here. It's an OLAD. This isn't torsion here.
Okay, I'm just thinking about like how the variables move forward.
Yeah.
So it would be temp that takes the next one first.
Mm-hmm.
Then it would be current.
Yeah.
Then previous, the update like that.
Yeah.
Like three things moving.
Exactly. So it's gonna go by line basis. Okay. So first it's gonna do this. We're storing that link. Right? We care about that link because we're gonna be breaking it, right? Because we're gonna basically say, hey, this one is end up gonna be pointing to none, right? So we want to save that link so we can come back to it. Okay. So that's what this temp is doing. This current.next, okay. This is saying, hey, we're telling this back to previous. We're basically reversing it, right? So now we're saying this is now pointing to the previous thing. Okay. So now so this breaks that link. Okay. But it's okay because we saved it in the temp, right? So we're saying, okay, our previous is now our current. So now we're moving previous up by 1. Okay, because now we've already got the previous before, right?
So at this point, current the current and previous.
Current will be basically the next node, and then previous is going to be the node we just kind of did. So it's going to be like this. This is this left. So my left hand is previous. This is current. So it's like over here. Okay, it's gonna start over here. Previous. Okay, this is gonna be none. Then it's gonna do this. Then it's gonna go over here.
Yeah.
And then.
It's just so it was
Yeah. Current.next previous. That's just saying, hey, this is now because we're like remember like here we're just kind of reversing the pointers. The pointer, so this pointing to the other thing. This is pointing to the thing behind it. This is pointing to the thing behind it.
It's just that line that I wasn't getting a picture of it. But yeah, I see it.
Yeah, exactly. Exactly. You see, like here, like literally this entire thing, all it did was you see it just kind of changed the arrows. Yeah, that's what the program did. So we would need to keep track of the previous. But if this was like a doubly linked list, then it'd be pretty easy, right? Because then we don't have to really keep track of a temp because then we could just access the forward and then we can use that to access the backwards. So it'd be like I guess more intuitive. But this one gives you as a singly linked list, so we'd have to do it like that. Does this problem make sense?
Yeah.
Okay. Yeah. So you can see, it beats 100% because this is like this is the optimal solution here. The unoptimal solution here would be turning this into an array, reversing that array, and then going through that array and making it into a linked list, and then returning that linked list. Now, what do you think the time complexity of that would be? So let's run through it. So like the first one, right? It would be turning it into an array. So to do that, you would have so that would be O of n, right? Because you have to iterate throughout the entire linked list. Okay, so now you have the array. Now you have to reverse the array. Okay, and then after that, after you reverse that array, then you would have to turn to a linked list, right? Which would be you'd have to go to that array again. It'd be O of n, and then you just have to return that new linked list, right? So that'd be like O of like what 3 of n, 4 of n, what? But so it would still just be it would be O of n, right? So because that's how we care about. But you see how we did like a 4-pass solution. So like obviously it's more intuitive, right? Like a O of n solution is faster than an O of 4 of n. Like because you're doing less passes. We're doing like 1 pass, right? A 1-pass solution is like, would you rather do something right like in one go, or would you rather like keep on going back like you just do it in one go, right? That's faster. So the time complexity doesn't change though, right? It's still O of n, but our space. So are you familiar with space complexity? Yeah. So basically, well, what's happening is so if we're making a new data, so an array is a data structure, right? We're making in a new data structure that's essentially the size of this linked list, right? Which is n. So our space complexity would become, well, what do you think? It's still big O. Like it would be big O of what? Worst case, it would be big O of n. Right? Because now, let's just say we have an array. This array is now the size of this linked list. So now we have an array of this size. We've taken up n space, right, in our program. So that our space would become an O of n. If we did that array solution. But here our space is O of 1. You see, because we're doing everything in place. We're not creating anything new. We're just creating these variables, but creating variables by themselves is just O of 1. Because yeah. You're not storing anything. So you're not storing like any. You're not because this is just holding one thing, right? Like these variables are storing one thing. The array would. Yeah. And then arrays would just hold the entire thing. Like it will hold the entire linked list. So that's why this is optimal. So you can see here we analyze time complexities to say O of n. Slow. Okay. Yeah. So it's just linear. Okay. So that was this problem. This is like a really popular problem. So okay. Now we have merge two sorted, or maybe I might skip this one, and I might do add two numbers with you guys. It's a medium. All right. So I can just pull it up, and then we can just go from there. Okay. You guys want to give it a read? So like looking okay. So this type of problem, you know what I'd say, like it might look a bit confusing, but I will tell you this: when you add stuff on paper, right? Like when you just put two numbers, like imagine these as two numbers you put on paper: 243 and 564. Yeah.
I think like want to make it one list, so you put like 2.5, 4, 6.
Well, I mean, like if you kind of look at what this is doing, right? It's just adding, right? And it's doing it in reverse order. So like this. So we're saying, okay, this 3 plus 4, okay, and then that would give us 7, and then we're doing this 4 plus 6, okay, and then that would give us 10, and then that would carry over to here, and then that's 5 plus 2, that's 7 plus 1, 8. Right? So literally, so you saw kind of what I did. It was literally just the algorithm when you add on paper, right? Like you have to have a carry, right? Like the carry is gonna carry over, right? But then we're basically just having these pointers, and they're just adding. They're just adding the numbers inside. Yeah, and you see, so we would actually end up having to create a new. Yeah, exactly. It's just reversed, right? So this problem, okay, it's literally like it's literally saying, when you add two numbers, like when you put them like, when you say like 1, 2, 3 plus 3, 4, 5, and when you add them like this, you're literally just giving this algorithm to the computer. And basically to that, and like remember the computer is like a baby. Like you got to go really specific, right? So you're just saying how you would add this, right? And so remember when I was talking about like the pointers, and this is like this. So how would we add this? We would basically say, hey, we have a pointer here and a pointer here. We add these two. After we add these two, so that would be 8, right? Okay. We basically want to check: is there a carry here? Like, are we carrying? We're not carrying it, right? So then we can just move on here. Okay. Now with these 2 pointers are over here. Okay. So then we can add this. I'm just gonna make this of 8. Okay. So now these 2 pointers are here. This is a what? This is 6, right? We add this. There's no carry. Let's put that 6. Okay. Now let's go over here. What is 8 plus 3? Okay, so it's 11, right? So, but like, so we write that by just putting that 1, and we put that carry over here. Okay, now we move on. Is there a carry? There's that carry, right? So we'd have to move that 1 down, right? So you see how we just added? We did something really elementary, but we have to do it so that the computer understands, right? So let's think about this here. So, okay, first things first. We are gonna have to create a new, because this gets us a new number, right? You see how this is like its own thing, like it's gonna be separate from this and this. So we're gonna have to have a new linked list. Okay, so we're gonna have to have a new linked list. Now I'm gonna introduce you to something called a dummy head. So a dummy head is just like, it's literally what it says. It's literally a dummy, like you just kind of use it just to simplify whatever problem you're doing. You know, so what this is looking like, right? So this 1168, right? This is, I'm gonna erase this. So essentially what this is looking like is there's a dummy here, okay? 1 1 6 8. It would just be reverse order, but I'm just doing this to show you. So this is just the dummy head. So this just kind of simplifies it, because now we can say, hey, we can just kind of append. We can keep on appending here, and then we can basically say, hey, we don't care about this dummy head. And then afterwards, we can just say we can just return it from here. And you see, this dummy head just makes it easier for us to get to our actual answer. And then this will become the new head. So this is the actual head. But this is just like, this is the dummy head. This is what we're doing just to simplify our process.
So we added this dummy head to our existing list.
Oh yeah. So when we're creating a new linked list, right? So you could do this with.
Oh, you're saying that's the new list.
Yeah, this is a new linked list. Yeah. This is a new linked list. Yeah, and you see how easy, because now we can say with this dummy, we can just keep on saying, okay, because this dummy is it's a node, right? So we can say this next is this and this and this. Yeah, we can store it. It doesn't matter. It's because we don't care about this. This is just to make our life easier when we go about adding this, right? Because if we didn't have this, right, then we would say, oh, does a linked list exist? Oh, if it doesn't exist, okay, let's create it with 1. Okay, and then if it does exist, oh, so that means that this 1 exists. So you see how like it makes it more complicated. But if we have this dummy, this is really fast. Like it's like, oh, it's so easy, and then we can just get rid of it at the end. And then getting rid of that would just be O of 1, right? Because we just move over 1 time. So let's create that dummy. Oh, that's broken. Okay. So let's say dummy is equal. So you see how they kind of give you the variable for a list node. So we're gonna say it's just a list node. Okay. We're creating a new list node. Okay. So we have our dummy. Okay. We also care about our carry, right? So we should also initialize our carry. Our carry should just be set to 0. Right? Carry doesn't exist right now. Okay, we don't have to store new variables for list 1 and list 2, because once we like kind of add them, we're not going to come back to them. Right? So now we have the dummy and we have the carry. Okay, so now let's think about how long we want this program to go. We want this program to keep on going until what? Like until it adds up all of these. But remember how this case, the carry goes over, right? So we're basically saying like, hey, while L1 exists, like while we're not at the end of L1, or there's something for L2, or there's still a carry, right? Because then that means that we should keep on adding, right? Like that was why I turned this to 8, because this would end up getting the carry. Like these two are done. Like these two are done, right? We've gone through these two. but we still have this 1, right, which is the carry. Yeah, but this basically accounts for it because this is saying, okay, if so the way do you know like how OR works and like
Oh, so, no, I see what you're saying. So L1 can end before L2.
yeah, L1 can end before L2 or L2 can end before L1 or but or yeah. So we could say this, right? So okay, first things first. Let's keep track of the total. So the total is okay. So basically, total is basically what the variable we're gonna be adding everything to, right? So we're saying total is equal to carry here because remember, total should be whatever because we're gonna be setting this carry to whatever we need it to. Like if there's a carry, we're gonna be setting it to that, right? And that's outside. So we're this first total is equal to carry. This is saying is this what do we have left over, right? So if we have that 1 left over from the last one and it carries over, then our carry is 1 and our total is 1, right? For like this expression, it would be because we know we would add these two numbers. So that's why we're saying total is equal to carry. Okay. So now let's go into the case of if it exists, right? So if L1 exists, what do? We just kind of add it to carry, right? Like we're just adding that value. This is that first pointer, right? L1.val. And then what do we want to do with L1? Like we've think about this 3. We've added this 3 to total. Now what do we want to do? We want to move it to the next one, right? Because now we've added this 3. So now we just care about this 2, right? So now we would just say L1 is equal to L1 dot next. Okay? And it'd be the same thing for L2. If L2, we can say total plus equals L2 dot val. L2 is equal to L2 dot next. Okay? So now we've added these two, right? Okay? So let's think about this, right? So let's think about so we've added these. So now total holds out what we've added. Okay, so now it's gonna be like whatever number, right? I mean, at max it'll be 18, right? Because 9 plus 9 is the biggest number you can get. Like that'll be 18 because these are two single numbers, right?
I see how they add, but in the case, like let's say carries.
Yeah. So it'd be like this. So we're looking at this 2 and 5, right? So we add these. Okay, this will give us 7. We add this. Okay, so now we've added these two, right? So now we're at 4 and 6. Okay, we placed that 7. Okay, so now we add this 4 and 6. That's 10, right?
So total, total here.
Total would be 10.
And then carry is also at the end of that last bit. Then carry is also.
The carry will be 1. Remember, because we place that 0 here, and then we get the 1 over here. There'll be that 1 here because we do 4 plus 3. That's 7 plus that 1, and that'll be 8. So oh yeah, we didn't do that yet. Yeah, we're gonna be putting that now. So okay, so do you know what mod is? Like modulus?
like magnitude.
So it gives you like the remainder. So let's just say I say like what is 10 mod 3? So like what is the remainder of like how many times this like what's left over when 3 goes into 10 evenly? 1, right? So mod will return 1. Okay? So we could actually there's a neat trick with mod, right? If you mod any number by 10, essentially what you're doing is you're just getting that last digit, the last digit of that number. Now, that's really useful here because remember, we just care about that last digit. That last digit is what we're going to be putting in, right? So we can just say this. We can say digit is equal to total mod 10, okay? And then we can say, hey, our carry, okay? So our carry, so remember how we said 18 is the biggest number we can get? So what we're going to do is we're going to do integer division here, and we're going to say total divided by 10. Basically, this is saying, so let's think about 18, right? What is 18 divided by 10? Get rid of no decimals, like truncate the decimal. It's 1, right? And that's what's going to be carried over, right? So basically, this digit stores that 8 from the 18, and then this carry stores that 1. And then this is what's going to end up going over here. And this is what's going to add, right? So now we can say, so now you remember how we had this dummy, right? What happened? Yeah, percent signs for mod. Okay. So now we have this dummy. Now look how easy it is. We can say dummy dot next is equal to, we're going to create a new list node, okay? And we're going to call it digit You see how like easy that was? Like we don't, if we didn't have a dummy, we would have to do like we would say if this exists, we got to do this. If not, like, and it's like it's an unneeded, like a Boolean expression, right? So now we have this, okay? So now after we have this dummy is equal to dummy dot next. So now we want to basically, so now after we do this, so like we have this one now, right? Or we have this set this 7, okay? We set this, so this dummy is now pointing to 7. So now we should move that head up, right? That dummy. So now this should be the new like tail, right? And we're gonna be, because we want to keep on attending to the tail, right? So we're basically gonna move it up. So we're gonna say dummy is equal. Actually no. So we have this dummy here, okay? We want to have this pointer, because remember, if we get past dummy, we can't ever go back, right? So it should really just be, and then we're going to say current is equal to current dot next. This is what's going to be moving up, because now, so we've done this, right? And now you see, this is why we use current, because now we can just do this. Return dummy dot next. And then remember, this, we're basically returning this. And current, you see how before I was using dummy to introverse it, but we don't want to do that, right? Because then we won't ever have access to dummy again. And we have dummy there because like it makes our life easier. We no, see, so what it's doing under the hood is basically saying, okay, it's gonna go, it's gonna start this head and it's gonna go through the entire thing. Yeah. So like that's what like LeetCode. Yeah. So if we run this, hey, it's gonna run, okay, and this submits, and it should be most scores for all scores, 82.9. Yeah, okay, yeah. So, no, these test cases, 1,569. Yeah, but so you see this problem. Okay, this one I skipped the other one because I felt like this one is like more like I feel like you'd like it more because it's more so. So you see how this one we're just kind of we're literally just doing how we normally add, right? And we just kind of turn that into linked list. Like we just literally did baby instruction. Like this is, if you told a computer how to add, like, and like add the way we do, that's how you do it. So that's what, like, at the end of the day, that's what this is. You're just explaining very specifically on how to do something to a computer, like a baby. So that's what this is doing. And yeah, that's the use of this. So remember, mod 10, that will always give you the last digit of a whole number. Yeah, that's like always something that pops up. Did you take 111? Computer science 111? Yeah. So yeah, it's like always popping up there. And then this basically, this is saying, hey, so this basically lops off that last digit, because now we have the last digit, right? So we don't care about that last digit. Just lop that off, and then we only care about that next one, that carry in this case, which at most the biggest number it could be is 18 here, right? So then it would just become 1, and then you just keep on going. So yeah, that was this problem. Yeah, any questions? Yeah, it's a good one. Yeah. There's also a different variations from topic, similar questions. So this, okay, this isn't a linked list question, but this is literally the same algorithm. Yeah. Yeah. Yeah, you can search it by data structures. You can just go to problems.
I saw it earlier on was hash map one.
Yeah.
Is that recorded too?
Yeah, it's recorded. The hash map one and the 2-pointer one. Yeah.
Where was that?
I will show you right now. You're gonna see what I watch. All right. Queens College Learning Commons. Right here. Yeah, they're like
Chilling in the video right now.
you know that problem I just showed you, the add binary digits. It's literally it's if you watch a 2 pointer video and you like think about what we did here, you can solve this problem like easy because this is a 2 pointers problem, you know, like so this is saying string bit manipulation, but it's like it's not really like this would really just be like adding like this would be like pretty much the same algorithm, like you know where we have the carry and then and so on. So yeah, if you like watch the 2 pointer stuff and you can like follow along with that and like you understood this problem will be like easy. So yeah. This is my homework for you. But yeah, I yeah. Just that now. Yeah, no problem.
He said something about him getting paid.
I'm,
What?
I'm not
I
doing.
don't want to get paid.
That's true. That's true.
Nice guy.
Thank you, bro. Bro, I hope Bloomberg doesn't see this, bro. They're gonna see me fumbling on what reverse of.
Only 82%.
Yeah. Task host Windows. I don't know. I will. Dude, like